Okay, everyone, welcome to the Compass seminar. We are very fortunate to have this week Professor Andy Dessler from Texas A&M University. And Professor Dessler got a bachelor's in physics from Rice University, and then a master's and a PhD from the chemistry department at Harvard University. And Andy and I were at Harvard at the same time, and we believe we took a class together, although we have almost no memory of that interaction. Anyway, and then, that's right, is this National Research Council Research Association? Is that like a postdoc?
NRC postdoc.
NRC postdoc, okay, why do they call it? Okay, an NRC postdoc at Goddard. He's a research scientist at ESSEC, the University of Maryland, for a while. 1 year working, you were at the White House?
Yeah.
Oh, that's fantastic. 2000, 1 year of 2000 in the White House. Then he went to Texas A&M, where he's been an associate professor and professor. And he's a fellow of the AGU. He's a fellow of the AAAS. And he's won the American Meteorological Society Louis J. Batan's Author Award for his book, Introduction to Modern Climate Change. And I see on the back here, there's actually that book, also a book called The Chemistry and Physics of Stratosphere Ozone. That's from 2000. So that's a while. And then another one, The Science and Politics of Global Climate Change, A Guide to the Debate from 2019. So, take it away, Andy.
All right, well, thank you, Devon. All right, good. So this is a talk that's a little different than the stuff I worked on for most of my career. I spent most of my career working on sort of global climate physics, and then this happened. So this is the Texas blackout. Winter Storm Uri in 2021. Actually, it's just the 5-year anniversary of that. And this had a really profound impact on me. I walked out of my back patio, and in the evening there was no power on anywhere, and I thought, we are not prepared for this. And I don't mean that not prepared for cold, but we're not prepared for temperature variations outside the range that we're adapted to. We're really very sensitively adapted to a particular range of temperatures. And if you get outside that range, bad things happen. And while the risk is not extreme cold, the risk is extreme heat. And so but this was a good wake-up call for me about that. And I really thought that, this is what I want to work on. So I really spent the last 5 years working at the intersection of sort of physical climate system and human climate systems. So let's talk about electricity, because this is really where I got started. I walked out, I thought, how could ERCOT, who runs the Texas grid, how could they have screwed this up so badly that the entire state was out of power for days? And so let's do just a little history 101 of electricity systems, because I find that a lot of people have no idea kind of the history of this. So for most of the 20th century, electricity systems were these vertically integrated monopolies. So the electricity company owned the generators, they owned the transmission lines, they owned the distribution line, and they were a monopoly. And they operated in a certain area, and they were heavily regulated. They were regulated because they're a monopoly, and you can't charge whatever you want when there's no competition. And then in the 70s and the 80s, cracks started forming. And in particular, there were concerns that the price was too high, that we weren't efficiently allocating resources. And so utilities in the 70s, started to be required to interconnect and purchase power from other generators. And then this led to the separation of generation, basically separating from the rest of the utilities. And then this is sort of the beginning of it. And then you get to the 90s and the 2000s, where we really started seeing a change in the market design of electricity systems. And in particular, we saw the rise of these what are called ISOs, independent system operators, also sometimes called RTOs, regional transmission operators. ISOs, so that's what I'll call them, ISOs. And basically the ISOs operate the grid, and they basically buy power. So you have all these generators out there, it's a free market. They decide who to buy power from. They're going to buy power the cheapest. I'll explain how they do that in a second. But they go out, they buy power, and they operate this wholesale electricity market where consumers not you guys, but like industrial consumers and utilities go to buy power, and the power providers come and they match them up, basically. And then the utilities purchase power from the wholesale market. All right, so this is what a map looks like of the ISOs. So they're basically, you have ERCOT, Electric Reliability Council of Texas. This is where I live. CAISO, California ISO, Southwest Power Pool, Mid-Continent ISO, New York, New England, PJM, which is Pennsylvania, New Jersey, Maryland. And there's a lot of the countries white, including you guys. You guys still live under vertically integrated utilities here. So you guys don't have, so this doesn't really apply to you. What I'm going to talk about today doesn't apply to you. It applies to sort of the market places like ERCOT and CAISO. I'll talk a lot about those two particular markets because they're so big. All right, so let's talk about wholesale electricity markets 101. And this is all stuff, by the way, before the freeze, I knew nothing about this. I couldn't even tell you what ERCOT stood for. And then afterwards, I started just sort of reading about it, and it's very interesting. It's very cool the way it works. And once you understand this, you understand a lot of things about the way the world works, so pay attention. All right, so every day, the ISO forecasts the demand for the next day, and I'll show you how they do that later. But they come up with basically a prediction of what demand's going to be, based on weather, essentially. If it's hot, demand's going to be higher than if it's 90, it's going to be higher than if it's 70, and if it's 20, it's going to be much higher than if it's 90. And then each generator bids to provide some amount of power at a specified price. So every generator out there, coal-fired, nuclear, natural gas, solar, wind, they're all bidding in. And so this is an example of what the bids might look like. So you have 6 generators, interesting, or named A through F. This is the cost they're bidding at. Now, I just made all this up, by the way. And this is the production, how much they're going to produce. And so you can think of these expensive ones as like coal-fired power plants, and like these cheaper ones as natural gas combined cycle. And so what the ISO does is they sort them. They sort them by price, and they create what we call the merit stack, which is the order that ISO is going to pull generators and apply them to the grid. So the first generator they're going to get generator D because it's the cheapest one. It's going to produce 200 megawatts, and then they're going to go on down the list. And because they know the demand, let's imagine, for example, they predict they need a gigawatt of power. And this is just, again, Texas is like 50 gigawatts on average. This is just a small number. This might be, half of Houston, or maybe a quarter of Houston. What they do is they go down the merit stack until they get a gigawatt of power. And so they put the line right here, and they say, we're going to get power from all of these generators. This generator gets buckus. Texas is not what they call a capacity market. You only get money in Texas if you sell power to the grid. So generator C is out of luck. They get nothing, but these generators all get paid. Now the question is how much they get paid. It turns out, and this is the key to understanding this, the key to understanding a lot of what's going on. They get paid the price of this last generator, what people call the marginal generator. So the marginal generator sets the price that everybody pays. So in this example, the wholesale cost of electricity is $55 a megawatt hour. It's 5.5 cents a kilowatt hour. And the rest of what you pay for is transmission and distribution, things like that. This is just the cost of generation. All right. Now this is really the magic. The magic is that they set the price equal to the marginal generator, and that's why you'll often be able to talk about this is called LMP, locational marginal pricing approach. All right, so let's talk about how renewables lower the cost of energy, because you probably hear people say renewables lower energy costs. Actually, some people say renewables raise energy costs. That's wrong. Let me explain how renewables lower the cost of energy. So this plot shows the same merit stack, but I've added a generator G right here. Now, this is wind or solar. Now, when they bid in at basically zero, because their marginal cost of generation is zero. They don't have to buy fuel. So all they have to, so they'll take any price. They'll take $1 a megawatt hour. They don't care because they make a profit on any price. Whereas the fossil fuel plants, which I'm sort of implicitly assuming these are all fossil fuel plants, they have to buy natural gas or coal, so they can't bid in at zero. There's a minimum price, and if the price goes below that, they lose money. But that's not true up here. So anyway, so the wind and solar are bidding in at basically zero. So they're always going to get selected. So now, this is the cutoff is right here. And so we've actually cut off. So B was the marginal generator, and it was setting the price at $55. But now F is the marginal generator. And this means that everybody's now paying $40 a megawatt hour. So by adding wind and solar, you cut the wholesale cost of electricity because you're pushing expensive power, which was setting the price. You're pushing it off the stack. So now the stack has cheaper power. And the more wind and solar you add, you keep pushing expensive power. You push the most expensive power off the grid and you lower the cost. This is why wind and solar save us energy, or save us money. And just to give you an example of how this works, this is ERCOT data from August of 2023 or 2024. ERCOT data. So this is fossil fuel generation, and this is the price. And you can see that the price rises, as demand rises, the price rises. This is something I'm going to bring back repeatedly. And the reason is, as the demand rises, ERCOT has to pull progressively more expensive power onto the stack. So as demand goes, the price goes. And when you get up here, two things are, when you get to very high demand, 60 gigawatts, when you get up here, two things are happening. First one is ERCOT starts raising the price artificially as a scarcity, to signal scarcity in the market, because they want large industrial consumers to shut off. So you'll see the price starts rising. Also, they're pulling on extremely expensive, what they call peaker plants. Peaker plants are natural gas plants that only run about 10% of the time, about 1,000 hours a year. They run in the winter and in the summer. And that's it. And they charge a lot of money because they're only running 10% of the time. So but anyway, the point is here is you can see the merit stack in operation. Now, you might say, why am I plotting fossil fuel generation here? And that's because the marginal generator in the US on any network is almost always a fossil fuel generator. There's no place that runs 100% on renewables at all. The most Texas, there are some instances where Texas gets to 70% renewables, and that's the best it can get. But still, it's 30% fossil fuels, so those are always what's setting the price of electricity. It's the cheaper or the most expensive fossil fuel generator that they need to do that to satisfy demand. All right, so talk about the winners and the losers. So the winners are these people. These people are making money because their marginal cost is zero. They're getting paid $40 a megawatt hour. They are making bank. That's if you're a renewable generator, that's you on almost all days in Texas. The people who are losing are these people. These are typically coal plants. They're usually the most expensive fossil fuel plant. Nuclear actually is expensive, but actually bids very low because they all want to run 24 hours a day. So they're actually up here. It's usually coal is who gets pushed off the stack. And this is why coal plants are retiring in the US. If you ask the question, why are coal plants unprofitable to run? It's because they just can't compete with the other energy sources, so they get pushed off the stack. All right, so this kind of once you understand how this works, you understand 90% of electricity markets in the U.S. You'll see these things happen. It's like, okay, I understand why that's happening. So it was a revelation to me, at least. All right, now, and you can see this reflected. So this is a plot that ERCOT puts out. This is called the interconnection queue. This is the power sources that people plan to hook up to the grid. So this is gigawatts of power, and this is different fuel types. And the data look like this. And you ask, well, why? And I just explained to you why it looks like this. For solar makes a lot of money. So that's why 40% of the power that's planned to connect to the grid is solar. Because, the people building this are not Birkenstock wearing hippies who are traveling around in a VW minibus following fish. You know, these are people that want to make money, and this is how you make money. You do solar. Here's wind. There are some structural reasons why wind is a lot lower than solar. You can ask me if you want. This is natural gas. Natural gas is not a very good way to make money in Texas. And then I don't even know what other is, probably biomass or something. All right, you also notice batteries. So let's talk a bit about batteries. Batteries are really interesting. It's a really interesting problem. So I'm going to talk to you about some work that I have a master's student who sadly has decided he doesn't, given the current political climate's not going to get a PhD. But I think he has a very bright future working for energy companies who need to know about weather. Let's talk about batteries. And batteries are really interesting, a very, very interesting situation. So the way batteries work is they charge in the morning when power is cheap. When demand is low, the price is low, so they charge. And then they discharge in the evening when power is expensive. So a battery is basically like minting money. It's a money machine. It just, every day you turn the crank and dollar bills come flying at me. You buy low, and then 6 hours later you sell high. And so what we want to do is evaluate what the net impact of batteries on the wholesale price would be, and then how that might affect consumer prices. So this is another, this is a similar plot I showed you before. This is fossil fuel demand, so demand for fossil fuels, and this is the DAM is day ahead market. Don't worry about that. This is the price right here. So this should look, and each dot is 1 day, and this is from all the hours. You wonder why there's a lot of spread here. I have to talk. We haven't written this paper. You have to talk to him about this. He's basically pooled all the hours where batteries are discharging. So all the hours where batteries are discharging. This is the price. I think that makes a lot. We'll have to think about different ways to do it. But nonetheless, the message I think won't change.
Andy,
Yep.
I just want to ask, so the batteries you're referring to, are they the ones connected to people's houses, or are they like industrial batteries?
No, these are industrial batteries that are connected directly to the grid. That ERCOT, these are ERCOT, not people at home. ERCOT has no idea what they're doing. And similarly, the solar is not solar on people's rooftops. That's what they call behind the meter, which means you don't have the grid has no idea what you're doing. All it knows is you're not consuming power. All right, so here's a low S fit to it. And again, you can kind of see the same kind of hockey stick where it's so the price is rising, and then it gets, you start hitting market grid constraints, and ERCOT starts jacking up the price starts going up. And so we can evaluate, we can estimate what the price effect of batteries is. So in August of 2025 at 8 p.m., the average fossil fuel demand was 57 gigawatts. And that meant the average price was $75.96. Okay, so so far so good. But we also know that we were discharging almost 5 gigawatts of batteries. So batteries were pumping 5 gigawatts into the grid. If we turn those off, we would have to turn on 5 gigawatts of fossil fuels, because we're already using all the renewable energy we can. The grid's always using all the renewable energy. So the only thing you're dispatching at this point is fossil fuels. And if you do that, then the demand goes up to 62 gigawatts or something, and the price is $111. So we can say that in this situation, August of 2025, at 8 p.m., batteries saved us $35.77 a megawatt hour. That's a lot of money. That is a lot of money it's saving us. And again, the key is because this is really a very steep curve. The curve is very steep. So if you save 1 gigawatt, you're saving consumers a lot of money. All right, so this is the discharge part. But you also have to charge the batteries. So let's look at the charging half. So this is, again, ERCOT data. This is for all the hours that batteries are charging. And again, same plot, fossil fuel demand against day-ahead market. And here's the low S fit. And at 9 a.m., average demand is about 38 gigawatts, giving us a price of about $20.97 or $21. Now, but that includes the power to charge the batteries. But we know how much that was. That was about 4 gigawatts. So we were charging about 4 gigawatts. So if you turn those batteries off, you can actually turn off some fossil fuel plants. So some of the fossil fuel plants are running to charge the batteries. It's the cheapest ones, but they're still running. And that would save us about $3.50. And so we can sort of combine this. Oh yeah, okay, so just to explain why people are building so many batteries. So I said this before, they're buying power at $21 a megawatt hour, and they're selling power 6 hours later at $76 a megawatt hour, okay? Everyone understands that's a good deal if you're selling the power. Yeah, you're turning the crank, it is true. All right, so this is what we get for hourly savings in August of 2025. So this is hour of the day, so running from midnight to midnight. This is August 2025. Negative means it's costing you money. Positive means it's saving you money. And you can see that at 8 p.m., just 20 hours, you get the numbers close to what we got, about $35. And here at 9 a.m., it's costing us about $3. And so you can see this is really quite a good deal for consumers because it's saving us money. So batteries are definitely saving money for consumers in Texas. They're lowering. And in fact, if you go back to 2020, the thing that's kind of cool is we have built batteries really fast. So you can go back to like 2023 when there were essentially no batteries on the ERCOT grid, or I mean less than a gigawatt. And you can see incredibly high costs at 8 p.m. because at 8 p.m. the solar has gone down and they have to turn on all these very expensive peaker plants. And you see costs of hundreds of dollars a megawatt hour. And you don't ever see those anymore because of the batteries. The batteries keep us from having to turn on these really expensive natural gas plants. All right, let's look at CAISO. So CAISO, again, is California in ISO. And you see something which is a little bit different. I mean, it looks qualitatively the same, but it looks a little different. So you save 20 megawatt hours, or $20 per megawatt hour in the evening. Again, it's kind of similar to what we did with in ERCOT, but it's also costing you a lot of money to charge. And so this is kind of puzzling. And so we puzzled over this for a while. It's like, why is this looking different than it did for ERCOT? Why does California look different? And so there's a couple of reasons for this. And let's look at the two curves. We combine the two curves into one plot. Again, this is demand, and this is day-ahead market price. And what you'll notice, there are a couple things to notice. First of all, the demand is a lot lower. Okay, so California uses a lot less energy than Texas, and that's a function of Texas is a much hotter place than California, and Texas has a lot more industrial base than California does. So we build a lot more stuff, and so our demand is much lower, and they have a lot more batteries. So while you saw, I was showing you about 4 gigawatts in Texas, they have about 8 gigawatts. And so it is a big function of this. And so let's go over the numbers. So imagine you're up here, you're discharging 8 gigawatts. Oh, and the other thing to notice is these low S fits are basically straight lines. So it doesn't really matter where you are. This line is straight, and you discharge 8 gigawatts, and indeed you save $20. This is essentially what we showed with the ERCOT, and so we see basically the same thing. But you see that for the charging has the same slope. So unlike in Texas, where the batteries are charging on a lower slope because the curve's a hockey stick, here there's no hockey stick. And so let's say you're charging from there, you charge 8 gigawatts, it costs you $20. So there's really no net benefit to the consumer just in the wholesale price in California because they've gotten rid of the hockey stick. They don't have that really fast rise of the cost of power that Texas does. And I think a lot of it's because of batteries. The batteries have actually eliminated the hockey stick because they're there to keep you from having to turn on the very expensive power. But it nets out to not a huge benefit to consumers just on the wholesale price. Now, let me be clear. Consumers still benefit. They benefit because of all the externalities of fossil fuels. They're benefiting from less climate change. They're benefiting from less air pollution. They're benefiting from less price variability. Because once you build a solar panel, you know what the price is going to be for the next 30 years. You don't know that with fossil fuels. You have no idea what the price of natural gas is going to be next year. You don't know what's going to be tomorrow. So that's a bit. And again, let me just sort of compare that with ERCOT. ERCOT has this hockey stick. And what's going to happen, though, is as ERCOT builds more batteries, this hockey stick is probably going to disappear. That's our prediction, at least. And then ERCOT will get to the point where it's not actually saving consumers money on the wholesale price. Again, they're still benefiting from having fewer fossil fuels. So this is sort of a temporary thing as ERCOT builds out their, So just to sort of summarize this part on batteries, we find that batteries save money on the ERCOT grid basically because of the hockey stick shape of the price demand curve. And that's a function of several structural things, including the reliance on peaker plants, but also the rules of all the ISOs are slightly different. CAISO's evening savings are basically offset by the cost of charging. So there's really no net effect there. And that's basically because of CAISO's very large battery capacity relative to their demand. And it's reduced their reliance on peaker plants. But of course, even without direct savings for consumers, the economy still benefits from fewer externalities of fossil fuels. So now let's turn to climate change. So you guys don't want to hear just about electricity markets. Let's talk about climate. And this is something which occurred to me in the summer of 2023. Summer of 2023 was unbelievably hot in Texas. I mean, there was this high pressure system parked over northern Mexico, and it was just baking the state for months. And I opened my electricity bill in August, and it's like, holy crap. And so I go out and I turn the thermostat up. And then like half an hour later, my kids come out of their room. They turn the thermostat down. So we had a big fight over the thermostat. But it got me thinking about, this is a big problem. If for people who are at the bottom of the economic ladder, they spend an enormous amount of money on electricity. Electricity is one of their biggest expenses. And so I wanted to say, can we quantify the cost of electricity or the cost of climate change on their electricity bill? So the first thing we need to do is we need to create a relationship between energy and climate. So how does energy demand vary with climate? This turns out to not be nearly as hard as I thought it would be. This is what ERCOT gets millions of dollars to do, or hundreds of millions of dollars. So this is Texas average temperature. So we just average the temperature in Texas, and we population weight it. So it's really population weighted daily average temperature. This is daily average demand. And again, this is ERCOT data from 2023 and Era 5 land data. And this is what it looks like. So each dot is one day. So each dot is a day. And you can see here's very cold days, very hot days. The orange line is a fourth order polynomial fit. We put a categorical variable for weekends and holidays. And it's a pretty good fit. Average error is 0. And the RMS error is about 1.3 gigawatts. So you can predict. You tell me the temperature, I can tell you what demand's going to be. I mean, this is not rocket science. And so once we have this, we can now do the following. We can take the temperature from any year. This is 2000, and we can plug it into there. And I can tell you what the demand would have been if the temperature had been different. Oops. And so you take the temperature from 2000, plug it into here, and this is every day's temperature in 2023 if the temperature had been the temperature of 2000. So let me repeat that because I always get a question in the audience. Everything is 2023. The population is 2023. The generator stack is 2023. The infrastructure is 2023. The only thing we're changing is the temperature. That's the only thing we're changing. We're just taking 2000's temperature, we're just dropping it into 2023, and we're saying this is what the demand would have been. Put that up there, because and if you still have a question, I'm not saying you can't ask me, but I'm just saying I always get that question, so just try to head it off in advance. So it's the demand in 2023 that would have happened had we had 2000's temperature. And this is just to give you an idea of what the temperature looks like. This is the temperature of population-weighted Texas average temperature, and it was very hot in the 1950s. There's a brutal heat wave for the whole decade. I grew up in Texas, in Houston, in the 1970s. That was like the coolest decade of the last 150 years. I didn't appreciate it at the time. I'm sorry I didn't appreciate the actual temperatures. God, the amount my mother complained about the temperature, though. Anyway, and then you can see the temperature's going up. All right, and we understand that's CO2. I can take those temperatures, I can plug them into our fit, and this is a time series of demand. This is the weather year, so it's the 2023 demand, but with different weather years. So if I have 1950, demand would have been 48. And temperature 1950, demand in 2023 would have been 48.1. If I had the temperature for 1970, it would have been, 48.5. And, you can kind of see it's kind of flat. You can kind of see it's going up here. So we can now use this to estimate how climate change has affected the demand, at least climate change since the 1950s. And we're going to do that by taking a baseline, 1951 to 1980, and we're going to compare that to the last 10 years, which was 2014 to 2023. It's the data I had when we did this analysis. And the difference here is climate change. And so it turns out that climate change has increased demand by about 2%, 0.9 gigawatts. Now, you look at this, you think, 2%, what's the big deal? But remember what I said before. As the demand goes up, what else happens? Anybody? Price goes up. The price per unit goes up. So not only are you buying more power, but you're paying more power per unit. So you get hit twice. Higher demand and higher cost per unit. And so we can look at that. So here's 2023 data. And this is a slightly different fit. I told Austin he should do this, but he said, I want to do a low S curve. All right. But it's basically the same thing. This is daily average demand. This is wholesale price. And these are all daily averages. Each dot is 1 day. And you can see it kind of is reasonably smooth. Weird things happen in Texas, like a generator will trip offline, and that'll cause the price to spike in the area around the generator. And so that's what these are. These are like a transmission line fails, or a generator trips, or a transformer explodes. But basically, you can see there's a reasonably smooth curve, and then you hit a constrained region, and the price starts going up. And I cut it off. Their price is much higher, hundreds of dollars a megawatt hour. But there's definitely a point where the price starts rising. And again, this is ERCOT. It's partially pulling more expensive generators, but it's also them just raising the price to discourage consumption. So that is what they do. They did it famously during the blackout. They set the price at $9,000 a megawatt hour, and there's no reason to do that. It wasn't like the power was out. It wasn't like people could stop using power. It wasn't going to bring more generators online. But anyway, they did that. All right. So now what I can do? Oops. That's weird. Didn't update the screen. Let me hold on. Screen tempted to start. All right, I had a Zoom failure. Let me go to Zoom. Let me reshare my screen. All right, let me connecting. It doesn't look like maybe I'm not online. All right, I'm going to leave and reconnect. Sorry about this. It was working fine.
I think the network was a little unstable. I had a message on my screen as well, but I'm still connected.
All right, let me. Sorry, if this works, it'll be 30 seconds. If it doesn't work, then maybe I'm not online anymore. Maybe my iPad. It says I'm connected to the network. All right, well, tell you what. People watching online, you're out of luck. I'm just. So can we switch over to? I guess my iPad is connected on Zoom.
Yeah, try to get back.
Let me try. Okay, let me go to my settings. Sorry about this, guys. Wi-Fi out. Let me turn Wi-Fi off and turn it back on. Wi-Fi on.
Were you on the visitor Wi-Fi
Yeah, I'm on the
or EduRoam?
Cain's guest.
You can try the EduRoam.
Yeah, I have trouble connecting to EduRoam.
Oh, okay.
So it looks like it is not connecting to the Cain's guest account.
It's the FPL gremlins.
Yeah.
They don't want you to know that there's another way.
Oh, no, it looks like I'm connected now. All right,
Yeah,
so then
yeah.
let me go to this. All right, I will get this working in a second.
Yeah, so Brian McNulty writes in the chat that he can still hear you because the radiant here is still connected. But of course, it will be better
Yes.
if we get back online.
All right, hold on. All right, so there's the Zoom link. Let me rejoin. Zoom. Loading. Join. All right, it looks like I am back on screen. broadcast. All right.
Okay.
Brilliant.
All right. But of course, I lost my spot. Where was I? All right. Okay, so let's remind people, here's the price. This is what I think where things crapped out. Here's the price. So now we can do the following. So we can start with temperature from any year. We can plug it into our fourth order fit. And that gives us the demand on that year. Then, for any demand, is that from me? That's
my
your
message is
message.
showing
Sorry.
up there.
So
That
then,
was not-
once
not
we know the
intentional.
demand, we can then go and get the price. We can get the price by using these fits. And then we just multiply price by demand. And so for any day of any year, I can tell you what it would have cost if that year had happened in 2023, if the weather from that year had happened in 2023. And so now we can actually evaluate the full cost, not just the change in demand, but the change in demand convolved with the change in price. And so this is what it looks like. So January, we use less power because it's warmer. A lot of electric heat in Texas, warmer January's 12%. So climate change, yay. August though, you see the pain. It's an increase in cost, total cost of 44%. This is wholesale cost, not retail cost. But the wholesale cost has gone up 44%. That's a lot. That's a lot. And that way outweighs any money you save here. And if you go over the whole year, winter decline, summer decline. If you go over the whole year and do all these months, you end up with quite a large increase, 16% increase. And this is in millions. So this is $2.1 billion of total wholesale costs, 16% increase. And this reflects about $80. I don't have it on here. It reflects about $80 a person. If you ask how much per person is climate change costing you, it's about $80. If you divide that by 30 million, which is the population of Texas, 32 million, it's $80. That's a lot of money. Maybe not a lot of money for us, but a lot of money for people who are living at the very bottom of the economic ladder. Now, let's take a look at this plot again. And the thing you'll notice is that this hockey stick part of the plot really is important. And well, actually, go back. And so I sort of, so this is really a constrained regime that ERCOT puts on there to basically incentivize people to not use power. And so I said, well, how much is this constraint costing us? So we did another experiment where we took the constraint out. We just extended this line, which is kind of the natural slope of bringing on more expensive power. Just extended it. And then we redid our calculations where instead of having the price do this, we just let the price do this. This is sort of an unconstrained, there's no grid constraints in this case. In this case, we get this. It doesn't change January very much because the January demand in general is very low. It doesn't hit the constrained regime. The demand is just lower. Unless you get very cold temperatures, the demand never gets above 60 gigawatts. But you see in August, it makes a huge difference. And so what it says is most of this comes from the fact that the grid is going you're reaching the physical limits of the grid's ability to supply power, and ERCOT is raising the price. And so this actually says from a policy standpoint, this would be good if you could get rid of that constraint. If you could figure out some way, increase transmission, build more generators, do something so that we didn't have to have that constraint. You would save consumers a lot of money. You'd still be paying more, but it'd be a lot. The increase would be much lower, and that's also true for the annual amount. How are we doing on time? So let me see if I can. I don't know if this will work. I didn't realize we did this. Let me see how I play this YouTube video, which is.
Millions of Americans in the grip of this brutal heat wave are all.
Is that going out, or is that just coming out there? I mean, I can hear it's coming out this speaker. Is it coming out the speaker?
Yeah.
I'm not sure. That depends on what you are sharing. If you are sharing your sound, it will go into Zoom.
No, I'm sharing the screen.
Yeah, you can, usually when you start sharing the screen, you can choose if you want to share
Yeah,
the sound.
I'm not gonna worry about that because I will screw it up. And,
Yeah, they will hear it through the microphone.
So let me say, so a lot of the work I do now, whenever I work on something, I always think, is this going to be newsy? And you know, I don't want to be one of those scientists that sort of chases news, but I do want to do work on stuff that people think is important. So when this came out, I emailed a bunch of people I knew, and one people I emailed was David Schechter at CBS. He says, "Oh, let's do a story on this." So let me play. This is only 2.5 minutes, but it's a story they did on this, and it has some other results which I did because he asked me to do them. They're actually not in the paper.
So facing soaring costs to run their AC. Over the last 3 years, retail electricity prices have gone up faster than the rate of inflation. And at the very same time, new research from Texas A&M shows that our warming climate is making it even more expensive to cool homes. David Schechter looks now at the effect on struggling families.
I mean, with everything going up, man, it's hard to survive now.
Angela Harmon is raising her grandson Theo while also recovering from cancer. In the brutal Texas summer, she can't afford to keep their apartment cool.
How much do you worry about your air conditioning bill?
Some things get paid late, some things don't get paid at all to keep the lights on.
To pay her utility bills, last year Harmon relied on the federal government's Low-Income Home Energy Assistance Program, which serves more than 6 million Americans. But President Donald Trump's budget proposal for next year would eliminate it. In a comment to CBS News, the White House called it a failed program that is also mired in fraud and would leave it to the states to administer their own utility assistance.
It sounds like those funds won't be available next year.
Wow. Well, that's going to be hard.
And this is a hard problem.
Professor Andy Dessler at Texas A&M University studies the impact of climate change on consumers.
What did you discover in your research?
Well, I discovered that climate change is increasing the cost of electricity.
In the summers of 2023 and 24, he found climate change increased wholesale electricity costs by an average of 35% in New England, 30% in California, 20% in Texas, and 17% in New York. He says when it's very hot and demand peaks, the cost of electricity can surge, and those extra costs eventually get passed along to consumers.
You can directly draw the line from humans emitting greenhouse gases to the atmosphere, increases the temperature. That means people have to run their air conditioner more.
One bright spot Dessler found is solar power. It is the cheapest form of energy and can help push prices down. But he's concerned consumers will be hurt by Trump administration policies that slash renewable projects in favor of higher cost oil and natural gas.
It is going to make things much, much worse. It's going to be much more expensive.
As the planet gets warmer, we're paying more to keep cool. It's an added cost many Americans are able to afford.
It's on my mind every day.
But for Angela Harmon, it's making a hard life even harder. For CBS Mornings, I'm David Schechter in Dallas.
So, you know, the reason I like that, I don't like it. I mean, you know what I mean. You know, it really shows you the human cost of these things. These are not numbers like someone calculates convective entrainment rate or something. I mean, this actually affects people's lives. Not that convective entrainment doesn't, but you know what I mean. I mean, this really hits the bottom line of a lot of people. And it's a serious problem. The stories of people who can't afford electricity are really terrible. I thought David did a really fantastic job in that news story. All right, so what are the conclusions? So basically, climate change is costing us money. You know, no surprise there. There are lots of ways it costs us money, but this might be one that you hadn't quite thought about. 2023 saw the demand rise. Again, this is a direct, where we can draw the line directly from emitting greenhouse gases to warmer temperatures to demand going up. And then this increased total electricity costs by about $80 a person in Texas per capita. And this could be drastically lowered if we eliminated grid constraints. So that's something that we should be doing, and thank NSF for support. And I think it says preprint, but it's a reprint if you are interested in that. And to be honest, I'm not 100% sure that link still works, but if it doesn't work, email me. I'd be happy to send people the paper. It's in Weather Climate Society of AMS. Anyway, I'd be happy to answer questions. Thank you.
Will you walk around with it?
Sure.
Okay.
But I'm going to ask the first question. So, basically you should, the way the curve goes up at the high demand, and you, towards the end, the second half of the talk, you attribute it to ERCOT, like ERCOT does this.
Yeah.
But aren't they just doing what is done by that market system that you first described?
No, it's in addition to that. So
Oh.
it's in addition to that.
Oh,
But
that's-
they are,
okay.
it's
Got it.
they are taking the price and they are increasing it more in order to tell people to stop using power.
Okay, so
And
that's an arbitrary choice that they're making.
well, I wouldn't say it's arbitrary. It's a lot of it is constrained by the grid. So there are these like transmission lines are rated to carry a certain number of megawatts.
Right.
So if the distribution, you could have a lot of power in West Texas from wind and solar, and Houston demands a lot of power. You just can't get it there, and so they say we're going to start raising the price, and they do that even though the power is available. In fact, sometimes you'll look at a price. You can look at maps of the price, and West Texas the price will be $0, and East Texas the price will be $100 a megawatt hour.
Wow.
They just can't get so it's a constraint on the grid, basically.
So I mean, it does have some logic to it that if they didn't do
Oh,
that,
yeah.
then the grid could blow up.
Yeah, no, I mean, they're doing, I guess I shouldn't make it sound like they're just doing it to be mean or something. I mean, they're doing it because the grid is reaching its physical capacity.
Okay.
They can't supply all the demand at a lower price. So they start ratcheting the price, and they hope people react to that.
Okay. Are there any other questions?
Nice talking. In the CBS clip, they showed New England
Yeah.
and New York and stuff, and they had very large increases as well.
Yes.
And I would have thought that there would have been more of a trade-off between the heating and cooling in those colder climates.
Yeah, so that's it. So that's actually what I would have thought. So I did all of those calculations because they asked me to do them. They said, "Oh, this is great, but can you do?" As I said, "Sure, I can just rerun the code for other ISOs." So it turns out that the southern U.S. has a lot of electric heating, whereas the northern U.S. doesn't really. Like if you go to Boston, I think that may be changing in the future, but it's a lot of people are using oil or natural gas like that. So that's really what explains it. Because if everybody had as much electrical heating as Texas does, then the northern place would be saving a lot more energy in the winter. But they're not, because they're not using electric heating.
Okay, I see.
Yeah,
Okay.
yeah. A lot of go ahead.
Quickly.
Oh, okay. So the projected increase in AI data centers and stuff, have you
None
thought
of
about
that's
how
in
that-
there. So I actually have a student who's working on that right now. We're working on that. It's very hard. What you run up against is it's extremely hard to get data on how much data centers are actually using. And so there are these people, for example, that take satellite images and they're counting the number of air conditioners on the roof of the building to try to figure out what the power dissipation is. Because you can't get, like ERCOT won't give you that power. They'll give you the power at nodes, but the nodes have lots of demand going into that. So you can't isolate the effect of the data center. But certainly, the data centers are driving up costs, because they're increasing demand. Increased demand, price goes up. So data centers are definitely doing that. Bitcoin does that. I actually wrote a paper, or we wrote a preprint on Bitcoin, and we put it out there. We got so much shit from Bitcoin people. And we just decided, it's like, look, I'm not getting any money to do this. My student felt he was kind of bruised by all of the harassment on Twitter he was getting from these Bitcoin army out there. We just kind of dropped it. But Bitcoin's the same thing. Demand goes up, price goes up.
Well,
Thank you. That was all very interesting. I was wondering, you talked about how there's kind of different systems depending on the regions in the U.S. for how energy prices are set, and you kind of pointed out those white portions on the map of the U.S. Is that something that you'll be looking into in the future as well, how energy prices are changing in those areas with different kind of cost systems?
Yeah, I guess I don't have any plans to look at that. So the way vertically integrated monopoly utilities work is they have to go and there's like a utility commission, and they have to say we want to raise rates, and they have to, and they get some return on their investment. So their incentive is to build the most expensive crap they can. So because if they build a $30 billion nuclear power plant, they get a return on that, and so they want to. And so those monopoly utilities are some of the worst offenders of stopping the energy transition. They hate solar roofs. They hate anything that's cheap. They hate cheap energy. They hate people generating their own energy, all that stuff. So it's a much more political system. I don't know that I have any hypotheses to test with that, because it's completely different.
Thank you.
Any other questions?
No, license.
So you talked a lot about like the ends of the curves, how like those extreme days, particularly warm days, are the ones that spike it the most. When we're looking at climate change and the overall like, oh, in the summer when you take out the inflated prices, you're still seeing like around 12% increase. How much of that increase is attributable to those like specific days where you have those extreme heat waves?
That's a good question. We haven't broken it down by temperature. I mean, that's I think it would be, because it's a quadratic or it's a fourth order, but because it's nonlinear, obviously the hot days are going to weigh more than the extreme days are going to weigh more than the moderate days. I don't know how much exactly though.
Someone over here? Oh, Liz.
In one of your previous graphs, you had detailed the population-weighted daily average temperature. Could you explain that in a little more detail, what the population weighting of daily average temperature would imply?
Sure. So we take the ERA 5 grid and then we clip it using GeoPandas to the Texas border, and then we multiply. We weight every temperature by the population at that grid point. So there's a lot of population data sets you can get. I can't remember which one we get, but there's U.S. government has population data sets. So we weight it by the population, then you do a weighted average, basically.
So that's on like a 25 kilometer, 0.25 degree, or what? Your ERA 5
It's
temperature?
ERA 5 land, so it's 10 kilometers.
Oh wow, okay, I didn't know that. Yeah, all right.
This is kind of an out of left field type of question, but when you're talking about like the solar grid specifically, when those companies come to your house and say, we will put solar panels on your roof, and in exchange you get a decrease in your monthly power bill, are those included, or is it really just the big solar farms and that $0 estimate?
Wait, so which estimate?
Like across the U.S., there are companies that will put solar panels on your
Right.
house in exchange for lower
Oh,
electricity
okay.
costs.
I understand what you're saying. No, so all of that is what they call behind the meter. So anything that happens behind the meter is not influencing the grid. The grid is just looking at demand. That goes through the meter. But if you put solar panels on your roof, and then you just consume all the power, they never know. They just see low demand. So that's not affected. So that's not none of this analysis includes that.
Thank you.
But aren't there arrangements where your solar power does go back into the grid?
Yeah, so right. So most of the time when you hook up solar panels on your house, if you have excess power, it gets pushed back to the grid. They call it net metering, and you get paid some amount. Sometimes it's the full retail price. Sometimes it's the wholesale price. You get paid that. So in that case, that would. That's a good question. How do they account for that?
It would have to reduce the amount needed, but it probably very little.
Well, I mean, it doesn't. So it wouldn't affect the demand, because the demand is the power going out the meter. But I think, I don't think that would have any effect on any analysis I do here. I think ERCOT does break that out. If you look at the fuel mix tables, they do have what they call distributed energy resources, which would be basically rooftop solar.
Okay. Any other questions? John?
Yeah. Thanks for a great informative talk. There is effects behind the meter. FBL is a utility that is a monopoly, but they, through public service commissions, set your rate in ways that ordinary people wouldn't set, and clearly they're friendly people, but they also have influence on what you can install on your roof. So I tried to max out a 10 kilowatt system, and they kept nickeling and diming me and harassing me, and they make it very hard to get things permitted. And how they do that, I'm not exactly sure.
They want you to buy power from them.
Yeah.
What's in it for them?
That's
You
pretty
generate your own
obvious.
power. Yeah, no, as I said, utilities, there's a good book by Leah Stokes called Short Circuit that goes over utilities. They're the worst. Utilities, these monopoly utilities are just the worst. anything worse
No,
for the
anyway,
energy transition.
but thank you for your work. This is really interesting.
Oh, thank you.
Yeah, great talk. Do you see humidity-induced impacts on the energy demand?
Yeah, I mean, that's an interesting question, and a lot of people have looked at that, and the answer is that dry bulb temperature seems to explain most of the variance. So yeah, it's not, there does not see, I mean, it might be that there is an effect, but it's aliased into temperature, like the variability of humidity and temperature are correlated, so you just don't see very dry days in Texas in the summer. It's every day is humid, so we don't see that, at least in the statistical fit, whether it's there in real life or not. It probably is, because I think it does take more energy to air condition humid air than it does to air condition dry air.
Roland, you have a question?
Yes. Very interesting presentation. You focused very much on the reduction of costs for the consumers by using renewable energy and the batteries, but you didn't really talk much about how profitable those solar farms and wind farms and battery farms are for the companies that operate them. Can we assume that they are having a good profit from the way this is currently working?
Yeah, I mean, I think if we go back to this plot, this actually answers the question. This is the market. The market is speaking. If solar didn't make money, I guarantee people would not be installing it. They're not doing it to be good. They're doing it because that makes money. Batteries, even more so. If it didn't make money, they wouldn't be building them. So I think it definitely is profitable. And and part of this is there are subsidies, and so that does play into it. But I think solar has become so cheap that actually it's still going to be profitable even without subsidies.
Okay.
Oh, one in the back. One.
I like the feeling of the, but I'm also curious about the spikes. So when you have more and more like extreme events, the grid and the generators, something like that, would also become more vulnerable to those extreme events. I was wondering, are you guys doing any estimates looking at the increase in the frequency of the extreme events, the impacts on the grid, and also the impacts ultimately on the price?
Yeah, so far all we've done is retrospective analysis, taking ERA 5 and running previous years through the grid. So we haven't looked forward at it. It is extremely hard to look into the future of energy because 3 years ago, nobody thought about AI data centers. The forecast, ERCOT puts out a 10-year forecast for demand, and it's doubled in the last couple of years for what the 2035 demand is going to be. So the short answer is we haven't done that. I think that's an interesting question, but it's really hard.
Oh, Eric. Have you thought about like infrastructure costs related to wind or the event that you started with in 2021, the ice storm?
Yeah, so that is something we did not include the cost to build transmission lines. So the story that people don't know is why Texas has so much renewable energy is because in the 2000s, Rick Perry, who was the governor of Texas, championed building a big power line from West Texas to East Texas. And they called it the CREZ, the Competitive Renewable Energy Zone line. And it was essentially paid for by all Texans. Every Texan got a bill on their electricity bill to pay. And it was probably a few $1 billion. And without that, we wouldn't have nearly as much renewable energy. Because you can't get the power from West Texas where you generate it to East Texas where it's consumed. It's of no value. So that certainly is a cost. And if you want to evaluate the total cost or how much money renewable energy is saving you, you would have to include that. Now, we didn't really do that calculation here. We were really doing the calculation of just if we took a previous year and put it in, we're keeping the infrastructure exactly the same, what the change would be. So that's an excellent point. And if you do want to calculate the cost of renewables, you have to include the total the total cost.
Thank you. Okay, that was a great discussion. Let's thank Andy Dessler again. Got a couple meetings, and then we'll be in the wet lab for a little while later.